this is the review for the quiz that will be on absolute and conditional convergence. And so I already pointed out that the homeworks on this topic, this is some, if you want, this is from 5.5, right? And so the homeworks from 5.5, the homework review that I also posted today, is also a preparation for this quiz. But I want to do two more problems here. And I want to point out that, okay, when you did, there are two things you have to do, right? The alternating series test, which is part of 5.5, but there's also tests that you have to use from previous times. And in the homeworks, it was always the limit comparison test, but I want to do now one where you need to do the integral test as well. Okay, so here are the two that I want to consider. So that's the number. The first one is this one, so minus 1 to the n squared plus 4 over the 6th root of n to the power 17. Just to give you a little bit of ugly numbers, okay? So, step 1, alternating series test, because it is an alternating series. There are some other conditions, remember, this, and it has to be decreasing, it has to be positive, it has to be continuous, but all that I said, don't worry about that, it always will be okay. All right, so the limit for n going to infinity of, well, the thing without the signs, that is this. And now we have to do this limit, it's always the same thing. We look at the highest power. Let's see what's the highest power here. That would be n squared. What's the highest power here? That would be n to the power 17 divided by 6, which is almost 3, right? It's a little bit less than 3. So this is the highest power. So we're going to have to use this one, okay? So let me get space again. Oops. Okay, so I'm going to divide by n to the power, or perhaps let me write it as the 6th root of n to the 17th, and here also the 6th root of n to the 17th. Now, this is a little bit uglier now on the calculation at top. And so, so let's work that out, what you do. In the bottom, we kind of know what to do there, so I'll do that first, because that's just a calculation inside this root now, radical, and 17th, n to the power 17 over plus 5, divided by n to the 17, so we know what cancels here. Now, what do we get at the top? Well, let's just, as I said, I wrote it this way if in the bottom, because I want to put it in the side radical, but on the top I have to use the radical part, 17/6. So what happens if I divide by 17/6? Well, you get, so we have now, so this I'm going to, okay, let me write it up, and then I'll say how you calculate this, right? This plus 4 over n to the 17th over 6. Now remember, the whole deal, the whole reason why we divide by the highest power is so that we all get reciprocals. Powers of reciprocals that all go to infinity, to go 0 if you plug in infinity, okay? So what are the, so let's now look what we get, what we have here. So let me scroll this up. I want to write this reciprocal, that's why I'm writing it as a power in the denominator. So I have 17/6 minus 2. That is, 2 is 12/6. So it's 17/6 minus 12/6, which is 5/6. And that is a positive power. That's the only thing that matters here. So this will go to 0 if I plug in infinity, and the same here for the next one. And in the bottom, what we have there, just see what we get. Okay, 1 if it divided here, but we also have to divide there, 5 over n to the 17th. And so, but my point that I was making all the time, we have n to a positive power. These are positive powers, each of them. So each, if I plug in infinity, will go to 0. And so I'm left with 0 over 1. Don't forget, right? On the top is 0, but in the bottom we have a 1. Otherwise, we problem, right? If the bottom would be something else. Okay, so this is 0, which is okay. This means this is already convergent. But step 2. What about absolute convergence. Okay, in this case, we have to now first decide what Bn is, because we are dealing here. Yeah, perhaps let me write up the series and I have it here also, it's easier. So the question now is, what happens if I ignore the sign, right? And then we are talking about this series. So that is, again, limit comparison that I'm going to use. And so the Bn that I'm going to propose, we have discussed this last time, that was an n squared, that was the highest power here, and the highest power there comes from this term. So that is that. Here, in this case, we don't simplify or don't rationalize, and we just, because we have to calculate this limit. That was the next step, right? And that limit, we always do the same way. It's a little bit a special way that we do this here. N squared plus 4 divided by n squared, right? Top of An divided by top of Bn. And now, bottom of An divided by the bottom of Bn. And then top is very easy to do, and then the bottom is actually also easy if you bring it inside the radical. You get 1 over 4 n squared, and in the bottom I get, so this is an n, right? So I get the 6th root of n to the power 17 plus 5 divided by n to the 17th. So one more time, limit for n going to infinity. 1 plus 4 over n squared on top, and in the bottom I have the 6th root of 1 plus 5 over n to the 17th. All the reciprocals go to 0, but this time you don't want too many to go to 0, because you have to end up with something that is not 0, right? Now we get 6 power this one, right? But that's 1, which is definitely not 0. So it means, okay, so this was a good choice. So now we have to, so now look more, look closely, right? Let me say it this way. Look closely at Bn. So what is Bn now? Bn is n squared over, that write it already in a rational power. And I want to write it in the form of the P series, which means again everything in the bottom. Minus 2, which was 12/6. We had already actually did this calculation a little bit. So P is 17/6 minus 12/6, which is 5/6, which is still less than 1, so divergent. So this is an example of a series that was CC. Okay, no? I'll do one more example now, but this time using a different type of function. So that's the formula, I mean. Let's look at this guy. Minus 1 to the n, 1 over n ln of n squared. Yeah, notice that I kind of was sloppy here and do not always write down what the pounds are, but here, just to make sure that the denominator is well defined, I should start from 2. If you think about it, I cannot put in 0, I cannot put in 1 there, but that's, we kind of ignore this part, because that's really, as we already mentioned, never plays a role where we start from, whether this converges or not. Okay, so I can do again the alternating series test. So step 1, alternating series test. But this is so, it's very quick, so let me do it quickly. But in fact, you don't even need to do this, but that's something you don't know yet. So what you do is you take the limit for n going to infinity over 1 over n ln n squared. Now if I plug infinity, that's all in the bottom, right? So I get 0. So yes, it's convergent. So it was easy to do, so why not do it then, right? Now comes the absolute convergence question. So what we have to look at is at this guy. Now this is a mixed form, right? I mean, there's ln's in there. And okay, we have to talk today about the ratio test. So that's a test you could also use, but I said I'm designing it so that you can only need to use the stuff from before, which is in this case the integral test. The comparison, limit comparison test you should not use, because ln is not really a P series and it's also not a geometric series. Okay, so this means what? This means that I should look at the improper integral, so here we go from to infinity, so there's the same bounds here, of the corresponding function. Okay, and always immediately do this. If you have an improper integral, write it as a limit of a proper integral, which means that you now have endpoints on which the function is well defined and continuous. Okay, good. So I'm going to do the indirect integral again. Let's do this somewhere here. The indefinite integral. Sorry, I don't know what I said there. This one. You might be tempted to say integration by parts because we have this ln x, but remember that's only for functions like logarithm and exponential that are in the top and very simple, not complicated. So definitely not squared and definitely not in the denominator. So no. But what works here, if you don't see it right away, think about it a little bit, is substitution. U is ln x, because the main point is that okay. This is the part that has the ln x in it. What is left is this 1 over x, and that will be exactly my du. Okay, so this is 1 over x dx. So now I can plug this, replace everything. As I said, the 1 over x dx, 1 over x dx. So if you want, I'll color it for you. This guy is this part, and that is just du. And then the other part, 1 over ln x squared, and ln x is u, so this is 1 over u squared. Or, if you want, u to the power negative u, and then the power rule, add 1 to the exponent divided by exponent plus c. What is u? U was ln x. So we get, that's now, it's normally you don't have to simplify, but when you have to work with things, it's sometimes better to simplify. So the minus just comes on top, and this u minus 1 is 1 over u, so 1 over ln of x. Remember, u is ln x. Okay, so back now to our integral. This is now the limit for t going to infinity of 1 over, oh no, minus 1, there was a minus, right? Yes, minus ln x between 2 and t, so that would be, let's plug it in, that's infinity always. Well, I have those, I'm going to run out of space if I do this, so let me just write it here. That is equal to the limit for t going to infinity minus 1 ln t, you plug in t, and now you plug in the other one, minus 1 ln of 2. Okay, this is not a problem. The problem is here, but it's also a very easy integral in this case. I could ask you an integral, a limit. I could ask you a limit where you have to do L'Hopital also, but this is not necessary because if I plug in infinity, we see what happens, right? This is going to go to 0. Ln of infinity is still infinity. So the whole thing comes out to be 1 over ln of 2, because minus minus. So what does this mean? Well, this means it is convergent, right? As long as this is a finite number, if this is not infinity, then we have convergence. And if this integral is convergent, then the series is convergent. So, final conclusion, don't forget that, right? Final conclusion is that, where's my series? No, that's my previous one. Here it is. This series is absolute convergent. All right? So, that's for the test next Tuesday.